Hello. In this video we'll talk about quantum observables. As usual, we look at two cases, classical and a quantum. In a classical case, an observable is an n-dimensional real valued vector. In a quantum case, an observable is a n by n complex valued Hermitian matrix. In classical case, in order to calculate a mean value, you have just to calculate a weighted sum. In a quantum case, you have to calculate a trace of ρ by a. Let's look at an example of a qubit. Qubit can be thought as a quantum spin. In turn, a quantum spin can be described via three observables or three components, sigma x, sigma y, and sigma z, which can be represented by Hermitian matrices. These matrices are called Pauli matrices. We can also calculate mean values of each component and end up with a vector which is called a Bloch vector. Bloch vector is not only a mean values vector, but also an alternative way to represent a quantum state. Let's play a bit with the code and implement a couple of functions. The first function calculates a Bloch vector based on a state. The second function calculates density matrix based on a Bloch vector. Let's generate two states. The first state is mixed random qubit state. It's implemented here. And the second state is a pure random qubit state. It's implemented below. After generating, we can calculate Bloch vector for both two states using state-to-vec functions. Let's note that set of all possible density matrices forms a ball of a unit radius. The sphere, the surface of that ball, is a surface where all pure states lie. Let's look at our Bloch vectors. You can see that pure state, which is red dot 1, has a Bloch vector that lies on the Bloch sphere. In turn, a Bloch vector corresponding to a mixed state lies inside this Bloch sphere. It agrees well with the general statement that a surface of a set of all density matrices forms a set of all pure states. To summarize, a linear space of n by n complex valued Hermitian matrices is definitely a smooth manifold and can be integrated into Riemannian optimization framework. Thank you for listening the video about quantum observables.